My name is Shoja Chenouri from University of Waterloo. When I got invited by Sylvia and Abdul to talk in this conference, which I have attended several of the TIES meetings in the past. First, I didn't know what to exactly talk about, but then I said, okay, I have been working on the change point problem recently with several of my students, and also, of course, change point analysis is an important in environmental studies. So, and I said, okay, I'll talk about the change point analysis, more specifically, multiple change point analysis. Thanks to Abdul and Sylvia for the invitation. I will also thank the organizer of the TIES and the funding agencies, and the main goal, hopefully I can achieve that, is to advertise my students' work. So I have Ahmed Muzaffari. He is currently a PhD student working toward his proposal. Shahab just finished about a year ago, and he is currently postdoctoral fellow at School of Environmental Studies at Waterloo. Reza is doing postdoc at Mechatronic and Vehicle System Lab. Kelly took a job at York University as a tenure track assistant prof. And Greg Rice is my colleague at Waterloo. So, of course, if I go and wanted to talk about change point analysis, one of the famous data sets being used, an old data set, is Nile yearly volume, basically yearly volume of Nile River. As you can see, somewhere around 1897 or something like that. Yeah. So looks like there is a change point over there, because by change point we mean that the distribution or the process or data generating process has been shifted or changed at certain point, and that is the depicted there. So Abdul is in some way guilty introducing me, or kind of getting motivated to work on change point analysis by introducing me to a data set that it is, I think, from Turkey Lake about acid rain. There were different stations. They have been collecting the data. The data set I have is from, I think, from 1980s to 2003. Many stations, and this is one of those stations. By taking first difference of different characteristics or contaminants or pollutants, you call it, for example, pH level, Ca, alkalinity, and SO4, which is basically, in a sense, it's a multivariate data, and interest was that, okay, you can maybe individually analyze this and look for any changes or so, and of course, change point detection is respectively, it's helping you to see that if the policies you have implemented are working or not. So, but then that time the question was, okay, how do we analyze all of them together as a multivariate? So those days we didn't really much have many multivariate techniques for change point analysis, and that basically got me interested in working on change point analysis, mainly in the multivariate setting and non-parametric setting. And perhaps, as you can see here, for example, in the first difference, looks like there is some spikes there. So maybe there are outlying observations as well. So how do I take care of outliers as well in my procedure? How robust I can make the procedure, and so on and so forth. So my interest over the last several years have been basically in the change point analysis setting, and how do I do univariate data analysis or change point detection? How do I do change point detection when you have sensor data? For example, you have below detections. How do I do it in multivariate setting, functional setting? Of course, different types of data sets. As you look and work in the area, so you realize, oh, there are other types of data comes to you, and basically you don't know what to do. Okay, shape data, functional data, network data, these are all things that I have been interested. So change point can be done in online and offline fashion. So of course, in online fashion aims to detect a change as soon as they occur in real time. These are often called event or anomaly detection in the literature. Offline methods, which we basically have the data and retrospectively look at the data to see if there have been some changes because maybe the policies have been implemented and maybe we wanted to check the effectiveness of those policies. So we basically, in the literature, they sometimes call signal segmentation or breakpoints detection. These are the other names. There are many questions in the change point analysis setting, at least statistically speaking. So the question can be, did a change occur? Is there any change point? So that is basically single, you're looking for single change. Did more than one change occur? Okay, that basically brings us to the multiple change point setting. When did the change occur? So we wanted to basically do the estimation. With what confidence did the change occur? So this basically brings us to this inferential setting. For example, we wanted to maybe construct confidence intervals. Of course, application areas are everywhere you can imagine. So I like always to talk about a little bit of historical background, early works on the change point. So early work on the change point analysis goes back to Page, 2 papers and maybe more. These are 2 main papers, and Barnard. So these are around the 1950s. So the goal was to locate a shift in the mean of independent and identically distributed Gaussian random variables in industrial quality control setting. So that is basically starting point for change point analysis, and it was basically detecting one change. So that setup, a simple setup we have, is that you have IID or sequence of independent, so not IID, sequence of independent random observations. And suppose there is some tau, okay, which is unknown, and you want to see for any I less than tau, we have xi to be distributed according F1, and after tau, xi is being distributed according F2, and so over the time in the literature, distribution F1 and F2 could be maybe completely specified, meaning that we are only interested in basically estimating tau, okay? Or they can be unknown, and also you may consider parametric, non-parametric, so on and so forth. So if you notice, if I know tau, basically I'm doing a hypothesis testing problem. Okay, testing F1 is equal F2 or not. The thing that differentiates change point analysis from hypothesis testing is that I don't know tau. Okay, that is the only difference. So, and this is the one change setting. So, what basically one area of work or one approach to change point detection is basically using the Q sum or cumulative sum statistic, which is basically cumulative sum of some score functions. Score functions can be maybe observations, can be maybe the difference between xi and some parameter, and or log likelihood. That is basically what this has been done. So you're looking at Q sum of some score functions, and depending on you're doing offline or online, you will be basically looking at this kind of statistics, or you will be maximizing or maximally selecting the you will basically, in order to estimate or do any change point detection, you will be looking at the maximum of the certain statistics, which is based on the Q sum. And of course, Barnard did this some modifications here. I will not bother about those. Another approach other than Q sum was basically use early method is Shoja, which gave basically a Bayesian formulation to the problem, and assume that basically the change point is a random variable and has geometric distribution. So these are basically historical, a bit very early work on the change point. So literature on the change point analysis mostly restricted on a single change point detection, at least early on, up until 1980s. So you can see a lot of papers being published on the univariate setting in the single change point detection, discussing, mean shift, variance, covariance shift. I mean, of course, in multivariate, I included, that is the single change point detection, shift in correlation or in linear model, and so on and so forth. There are many, many nice textbooks on the topic. So that is a single change point detection. My interest is on multiple change point detection, which there had been a very few papers early on the multiple change point detection, but over the last 20 years, there seems to be a revived interest on the problem of multiple change point detection, and so many methods have been introduced, mostly in univariate setting. So in univariate setting, we basically have, we can write down the change point problem as a signal plus noise, yi equal fi plus epsilon I. Fi's are signals, ei's are basically noise, or epsilon i's, and you may assume that errors are normal, 0, and sigma square, and you're looking for to see if f has undergone different changes on some points. Let's say those are the points. If I say J0 changes at points omega 0 to omega 1 to omega J0, basically. I'm trying to find or estimate omega 1 to omega J0. So for example, if my signal is locally constant or piecewise constant, then I will be having this kind of maybe f, and then the data are basically scattered around each locally constant points. So the lines are basically locally constant. That is the mean function or the function f. And or it might be, f might be piecewise linear or polynomial. So we might be interested in to identify these change points, if there are. So how do I do, or how do we do generally multiple change point estimation and an inference? There are two approaches. One is a local approach, the other one is global approach. Local approach is basically you will be doing detection one by one, okay, which makes sense. One of the famous methods is binary segmentation. which you will basically starting by the full data set and identify one change if there is, and then split the data and go and investigate in each piece and continue. So there are fast to compute and conceptually simple to understand. And of course, easy to code, but good theoretical performance, which requires in this kind of methods stronger assumptions. So that is the drawback. So as I mentioned, binary segmentation is, as an example here, for example, you have this signal, it's a locally constant, so you identify, maybe you look at the whole data set and you try to estimate the first, maybe this is the one here. And then after you find this and you split the data to two pieces and you work on each piece separately and continue. Okay, that is binary segmentation or local basement. You can estimate all changes at once. So for doing this, you need to basically introduce a fitness measure. Okay, fitness measure for maybe for of a piecewise constant or piecewise polynomial signal. So these methods, which I will talk, they are accurate in theory with weak theoretical assumptions, but they are computationally slow. Okay, and it's not easy to basically work around, and they are very dependent on the quality of the optimizer involved. So along these lines, the first work that we did on the multiple change point detection is the work of Reza, which in this paper, which is already on arXiv, and a subsequent paper which basically does the inference problem or post-detection problem, or post-detection inference, sorry, is basically you look at, you're trying to use the idea of, lasso type penalization, basically. So what is the problem? If you, let's imagine your signal is piecewise constant, okay? You don't expect to have too many changes. The changes are, you're assuming to be sparse, okay? Most of the time, the difference between the function fi minus fi minus 1 will be 0. Sometimes this will not be 0, okay? So that brings us to idea of sparsity, and we are basically using some sort of generalized lasso type procedure here. As you see, we basically try to minimize this kind of criteria or objective function with penalty, which the matrix D depends on we choose matrix D in a way that what kind of signal we think might be there. Okay, is that piecewise constant, piecewise linear, piecewise polynomial, and so on and so forth, will be dependent on that. And of course, to do this, you can work with the dual problem and then do the primal dual relation to basically get the solution. So this example I showed was a simulated example, is basically doing that. Okay, simulated data in piecewise constant case. You see that the method basically detects around the right time the changes, and polynomial as well. I mean piecewise linear. One important thing is that many of the multiple change point detections using this have problem when you have a staircase. If you look at here, this looks like a staircase, yes? So they have problems in there. And this one is like a staircase if your signal involves that. So you will have issues regarding consistency, for example. So this resolves that problem. So that is basically one way of doing multiple change point detection. When your signal, you are dealing with univariate data and your noises are Gaussian, okay, or similar to Gaussian. So, but what if you don't have Gaussianity, or if you cannot rely on Gaussianity assumption? So maybe you would like to do some non-parametric procedures. There are, in the univariate setting, there are a few non-parametric procedures to do single change point detection. Okay, I mean, there are, these are the papers I found from 80s and 90s. So, which is basically using, as I said, the connection between the change point detection and the testing, hypothesis testing, basically will tell you, you're looking for Q-sum type statistic for doing change point analysis. So choose your score function to be rank, based on rank. So this is, these papers are using basically Wilcoxon type rank statistic, okay? So we kind of took those and extended those to the multiple change point detection in two of the works that I listed here. So the setting is that I'm not assuming epsilon k's are Gaussian, and I'm basically trying to estimate the breakpoint theta i's. So how much time I have? I may
probably we should try to.
Okay, wrap it up. So I will wrap it up. So this basically does the non-parametric, and I will be using those. And the nice thing about this non-parametric approach is that you can extend it to multivariate using the notion of center outward ranks, which are constructed from the depth functions, which I will not go over. So these can be extended to, although univariate, we have extended to multivariate, multiple change point detection, and even functional, okay? Which is basically the work of my other co-authors like Kelly. And so I have too many slides here, to be honest. I didn't intend to go over all of them. Just took my risk, say, oh, how much I can cover, okay? So yeah, there are some results, but I will, if you are interested, just email me, or some of these papers are already on archive or published, okay?
I think it's very interesting. I think it has many areas of application in the environment, and I think it would be good that you contact you to get these some of these articles and some of this work. It's actually it's a very rich subject. It's very, very, very rich subject. And I think we had Ian McNeil and Jim Biala and others from Canada. They have done quite a bit of work on the change point of problem. And we did some work, Sylvia and I, and it was published about regression model when you have a possibility of spread, and it was published in the Royal Statistical Society. So the subject is very, very interesting and require quite a bit of work, but the mathematics is very hard.
Yeah.
Thank you. We hope Amira is available.
Okay.
Otherwise,
Yes.
Oh, Amira is available. Okay. I can hear Cairo.
Okay, let me try to share. Is the screen working now?
Yes.
It is, yeah, it is working.
You can see my slides. Okay, good. And you can hear me well?
Your time. So Amira Layute is a graduate with, I think, I think we're the president of Thai, or the president-elect of Thai is. So it's nice to hear you, Amira. Go ahead.
Okay, thank you very much. And hello, everyone there in Canada. I think it's still morning. Here it's evening, actually. Sorry. So hello, everyone everywhere. Thank you very much, Abdel, for organizing this session. And I'm today going to present actually a joint work in progress with my co-authors, Hala and Ronia, on whether and how climate change may adversely impact children's malnutrition and their physical growth across Egypt using small area modeling. Maybe I'm not going to present a very heavily novel statistical methodology today, but applying this type of model to Egyptian data is very new and is looking promising for the decision makers. So according to a very recent report by the UNICEF, about 559 million children all over the world are currently exposed to high and frequent heat waves. And this figure will continue to increase, which is actually quite evident these days in Europe and in Northern Africa. And this will definitely require urgent action to protect the children from the adverse impacts of those heat waves on their health and well-being. It's evident that the continuous changes in climate will make many countries in the next 30 years experience more heat waves and extreme weather events, including both droughts and floods. And such changes in climate have great impacts on human health in general and on children health in particular. This can be actually directly through the emerging of water and airborne infectious diseases that are associated with high temperatures, or indirectly through affecting negatively the agricultural production, which leads to increase in the prices of food, leading to food insecurity, and affect also the income levels of those working in the agricultural sector, which will definitely affect the nutritional quality and quantity of children. According to the WFP, climate change could increase hunger and children malnutrition in the next 30 years by 20%. And unfortunately, low-income countries and poor populations are less capable of confronting the adverse impacts of climate change on children growth. Therefore, studying the impacts of climate change on children growth in the developing countries and in Egypt in particular is very important for better assessing the risk of malnutrition associated with climate change and for mitigating its effects and distributing the available resources efficiently. Malnutrition among children is one of the biggest challenges in Egypt that represent a huge burden on Egypt's economy. And malnutrition rate remains very high, with a stunting rate that stands at 21% among preschool children, according to the last Egypt Demographic and Health Survey. And there is no evidence for a reduction in this percentage in the last 10 years. It's not just that, but actually malnutrition is one of the health inequalities facing Egyptian children due to the large socioeconomic disparities across Egypt, which can even be exacerbated with climate change. Addressing the impacts of climate on children using aggregated data at the national level is not enough to unmask the geographical and population heterogeneities. And therefore, our main goal here was to study the socioeconomic determinants as well as the effects of climate anomalies on preschool children malnutrition across Egypt, allowing for both child-level variability and spatial variability across the different small areas of Egypt. So in this study, specifically, we aim at examining the association between climate anomalies and malnutrition among children below the age of 5 within Egypt at the individual level, and at investigating those impacts while controlling for the child socioeconomic aspects and both individual and spatial variability. We also wanted to investigate the geographical distribution of below 5 children malnutrition across Egypt after accommodating for the differences in climate from one area to another, and the socioeconomic characteristic, the differences in the socioeconomic characteristics also from one child to another. So this will be done through a multi-level spatial conditional autoregressive model. In our study, we relied primarily on data from the latest available DHS for the anthropometric measurements and the socioeconomic data of the children. Unfortunately, this is the last available one, which is in 2014, but we are aiming by promoting the results of this research for for a recent one to be published and available for data analysis soon. So the DHS data are geocoded, so that's one of the advantages of the DHS data, and the location of each child within a cluster in a certain area in Egypt can be identified. Whereas for the climate data, we have obtained monthly time series data for the temperature and for the precipitation from 1951 to 2013, which is the year prior to the DHS, from the Crew Time Series famous archive that covers the whole Earth at a resolution of 0.5 by 0.5, based on spatial interpolation of data from a large number of weather stations across the globe. So now, because the DHS data are geocoded, so we're able to do the matching between the DHS data and the surrounding climatic data. But actually, we did this merge. So basically, we identified the geographical position of the DHS cluster to where the child live on the map. And then we have drawn a circle of 10-kilometer diameter around this cluster. And we have averaged the climate variable over all the grid cells that intersect with this circle. Why we have chosen to draw a circle of 10-kilometer diameter? Because actually each child has been displaced to a maximum distance of 10 kilometers for privacy reasons. So that's in order to accommodate for possible changes in the temperature. So accordingly, the stunting the status here is our response variable, which is a binary variable that takes a value 1 for a stunted child relative to the WHO standard. And the primary variables of interest here are the average temperature and precipitation deviations or anomalies from the average historical data that a child may be exposed to in a certain area during his life prior to the DHS year. So two children living in the same cluster will not have the same values because maybe they are of different age. So they have exposed to different averages of temperature and precipitation deviations from the historical data, because we are, for example, maybe averaging across 3 years because the child is 3 years old, or averaging across 5 years because he's 5 years old. This is going to be in addition to some socioeconomic variables that might be a source of difference and variability in the stunting status, such as the child gender, birth order, and age, or the mother's education, BMI, or some household variables like the what toilet facilities available for the household, what water resource available, and the place of residence, in addition to some area variable that represent historical means for the temperature and precipitation. So historical means and standard deviations, actually. So since the response variable is a binary variable, then the stunting status of the child can be modeled as a Bernoulli random variable with probability of stunting pi ij. Then the or the log of the odds of the stunting is modeled as a function of the different socioeconomic and climatic covariates at both the individual level and the area level. The model will also accommodate for the geographic differences between areas across space through two random effects components. So one component is a spatially structured component, and the other one is a spatially unstructured random effect component. The spatially structured random effect components will account for the smooth variations in the stunting status over space that stems from spatial correlation as per this conditional autoregressive model. So given if we consider that W is an adjacency matrix where that takes one if two areas are neighbors and zero otherwise, then the conditional expectation of the spatially structured random effect is equal to the mean of the random effects in the neighboring areas, and the conditional variance is actually inversely proportional to the number of neighboring areas. So this, whereas the spatially unstructured component models the uncorrelated noise using IID normal random variables with mean 0 and precision parameter tau v. So the joint distribution of the spatially structured random effects is a Gaussian Markov random field that is centered at 0 and with a covariance that depends on the precision parameter tau u and the weighting matrix W. But unfortunately, because for each area, we have the sum of two structured and unstructured random effects, these two components cannot be seen independently, and so they cannot be they are not identifiable separately. And therefore, we use the reparameterization here that uses a scaled, spatially structured component and a spatially unstructured component. And here you can see that like the area specific random effect is basically a weighted average of the spatially structured and the spatially unstructured component, where the precision parameter here tau b is the one that controls the marginal variance contribution of the weighted sum of both. And phi is just like a weighting or a mixing parameter that measures the proportion of the marginal variance explained by the structured effect. So it's basically something that if it's very high, it tells us that there is a very high spatial correlation structure, and if it's close to 0, then there is no strong spatial correlation structure. So the model parameters here, whether the one of the linear predictor or the variance or the parameters of the variance covariance matrix of the random effects, are estimated in a Bayesian framework using INLA. So I'm not going into the details much more, but I'm just jumping into the results of the model. And you can see from the results here that the odds of stunting are higher among the males relative to the females. So among male children relative to the female children, and that the educational level and the nutritional status of the mother significantly affect the nutrition, significantly affects the nutritional status of the child. So you can see here that education of the mother as well as the father education also, and the BMI of the mother affect the nutritional status of the child. But there is no evidence for a significant urban-rural effect here. There is, I mean, it's insignificant. And also there is no significant evidence for the income. But stunted seems to be more prevalent among those who have no access to protected water resources. And there is a very huge difference in the odds of stunting among those with protected water resources versus those who doesn't have protected water resources. You can also see that the odds of stunting increases with age. What is mostly important here is that for the climatic variables, we found that in Egypt, both the temperature and precipitation anomalies over the span of the child life can have significant effects on the stunting status of the child. So this is in the sense that as the average temperature deviation from historical average over the course of the child life increases, the probability of stunting increases. Whereas for precipitation, there is more like an L-shape relationship in the sense that stunting probability tend to increase with reduction in the precipitation level across the child life. And this can actually be justified with the reduction in agricultural production and which probably causing food insecurity problems, but it's not yet clear what is happening as the child witness more rainfall than average. We don't, there is much uncertainty around this area. But actually this might be because Egypt doesn't witness a lot of rainfall and there is no much data in this region. For the spatial distribution of stunting in Egypt, it was found that the probability of stunting, that the posterior mean estimates of area-specific random effects and also the distribution of area-specific posterior probability of stunting are higher in this area, which is the east of the delta, and also a little bit in this area, so mainly in the north and the middle of Egypt, in an area called Beni Suef. Here, followed by this area that is called Suhag. And however, the data appear to be weakly correlated across space, highlighting that more spatial heterogeneities and disparities between neighboring areas is available, and that there is no clustering structure in a spatial clustering structure in the data. And thus the stunting status is more dependent on the characteristics of the child and the area where the child lives, but not on what is happening in neighboring areas. So this has been identified since the posterior mean proportion of variance explained by the spatial structure was almost 5%, which is the posterior mean of the parameter phi that measure the percentage of correlation structure, the proportion of spatial correlation structure. So in conclusion, we found that the result, we have found that climate change has definitely impacts on children's health, especially temperature, and that temperature is positively related with stunting rates. And so the impact of climate on children, and also that the impact of climate on child malnutrition doesn't only happen in a single direction, because it's not only that decreases in precipitation is associated with high stunting, but also increases in precipitation might be associated with high percentage of stunting, but we are not sure yet, and this actually requires further exploration. And that the other conclusion is that there are regions that are more vulnerable to child malnutrition, such as the area of Beni Suef, which was in the middle north of Egypt. And thus changes in climate can exacerbate the situation in these areas. And of course, these areas would need more attention. But these regions do not exhibit any spatial clustering, and hence they need just the area-specific targeted healthcare intervention that can vary from one place to another depending on the area needs. And current work now, we are currently working on examining how the effects of climate may vary from one location to another through the use of varying coefficient models. So that's what we are working on now, in addition to adding more complexities to the model that we have developed to account for other variability that might exist across space between children as well. So thank you very much, and looking forward for your questions.
Thank you, Amira. we have a few minutes for questions. Any questions? Yes, please.
Hi, I have a question to Nathaniel here. So just a question in terms of, I mean, the idea is you use your model for guiding interventions, right? But some may say that really what you need to do is address the root causes. Like maybe there needs to be more locally grown food in these in certain areas, poor areas, or you need to spray and control waterborne disease when you have areas of stagnant water. So when you're faced with communicating or take up or use of your model with decision makers, how do you discriminate between addressing the root causes or the use of your model providing interventions, say, in poorer areas?
I'm not sure how to do that.
Okay.
That's the problem. Maybe just walk that.
Yeah, sure.
Just sort of summarize that. Yeah.
I'll try to say that again in a nutshell.
Yes, please. Sorry. Yeah, I can hear you now better.
I guess my question is, you've developed a model and it's useful for looking at or guiding decisions to do with healthcare interventions, right? But one of the questions is, what are the root causes of the malnutrition, right? So would it be better for a decision maker to, start growing food in poorer areas to address that, or to spray for waterborne diseases in times where you have a lot of standing water? So how do you discriminate? How would you sort of promote your model between root causes and the intervention side?
Yes, thank you very much for the question. So that's actually very helpful. Well, so this was just a very preliminary results for the model that we were trying to develop. And basically, the idea was to look first at the socioeconomic characteristics and the effects of climate, or the effects of climate while controlling for the socioeconomic characteristics. But the thing is, there are, as you have seen, there are two routes. So there are indirect and direct effects of that might be present on malnutrition, and we are trying to get more data on these intermediate variables to try to identify whether the problem is in for example, in the food insecurity problem, or in what is happening to the environment, or it's due to the socioeconomic characteristics that are prevalent in the areas. And just the first preliminary results just indicate that there are problems that are due to the, for example, this area that I have highlighted here that suffer from large proportion of stunting relative to the other areas. So that's a very deprived area that doesn't have, that is having actually large percentage of poor people and not very educated people and so on. So there are these social interventions that needed to be done to this particular areas. But we are trying now to add more variables in the model to try to respond to to try to answer a question that you have posed.
I think they need the resources to be able to address this issue. And I think one of the things that I believe is missing in the model is the shift in the population density is not included in the model, and this should have been included in the model. What you are seeing from 1950 to 2015, a huge rise in the population. There was about 20 million in Egypt. Now we are talking about 103 or 115 million. And most of those people are coming from the rural area and located in Cairo, where there are problems. So I think this is an element that should have been included in the model, in my opinion. But it's a good result to indicate that. And the other aspect that the conclusions that is being provided, I am sure is available to the people who in the health and in the economic and all these aspects. And I think it would be available for whatever resources is needed for projection or whatever it is. But it's a very nice presentation. I enjoyed it. Is there any other question for Amira?
It's just a small comment. So here, Abdallah, I'm not doing a panel or a longitudinal study. So I'm not studying the a population. I'm studying the population in 2014, but I'm examining the effects of or the deviation of in climate, like how the climate has changed from like a very long times, for example, to now. Just because it's very hard to measure climate change, so we were trying to find a way to measure the changes in climate, or how climate is increasing, or what the temperature and precipitation are increasing or decreasing over time.
You are right, but I think the issue is you are drawing a circle of 10 kilometers about each child. And those children were born at different times, probably between 2015 and whatever it is. I don't really know what is the population size, but it doesn't matter. We'll discuss some other time. Any other question for Amira or for Shoja?
No questions. I'm just a follow-up comment to what you're saying. I mean, urbanization is happening all around the world. It's really rapidly increasing. And so, that would be an important effect to include, because it would enable your model to be more readily reapplied in other areas.
Yes, this is correct. And I think if you are looking actually the wide immigration that is taking place, and usually the people who have a little bit of resources for them to be able to immigrate and move around, the individual that is moving from the rural area into the cities, they have higher expectation. The one who are there, they like to live in the way that traditionally they've been living, and then if you have poverty, the poverty will continue. And I think this is the issue, but it's a very important topic. And the climate have very big impact on this. And I think the impact in Egypt is very severe, especially due to the water resources, because it's very limited. The population is increasing. The share of individual in the amount of water that they are getting is very little, and this is eating the agriculture. So I think it's a quite interesting topic that need to have investigation, and we should be investigating here in Canada for the people in the north and the native people, and see what is the effect on this subpopulation. Anyway, it's interesting. It's so we finish now, or?
Yeah, so this is the end of our morning sessions. Thank you, Amira. Thank you, Shoja.
Thank you, Amira. Thank you.
And for everybody